Let us recall that with each matrix A, we associated the following subspaces. So we have a row space, which we denote row of A. So this is a subspace spanned by rows of A. Then we have column space, which will denote col of A. So this is subspace spanned by columns of A. And finally, we have null space, so which will denote null of A. So this is solution space of a homogeneous system of linear equations AX is equal to 0. So today we're going to discuss these spaces and connections between them in more detail. We begin with the following theorem that tells us how elementary row operations affect each of these subspaces. So theorem. So 1. Elementary row operations do not change the row space of A. 2. Elementary row operations do not change the null space of A. And 3. Elementary row operations do not change linear dependencies between columns. Of A. Now, so what this theorem says is that when we apply elementary row operations to a matrix, then the row space and the null space do not change. But the column space does change. However, it changes in a controlled way. So what doesn't change is linear dependencies between columns. So if we have a certain set of columns which is linearly independent, then after we apply elementary row operations, this set of columns will be linearly independent. And if we have a set of columns which is linearly dependent, and then we can write down a non-trivial linear combination of these columns that is equal to a 0, then in the new matrix, the same linear combination of the same columns, or of new columns, will be 0. So this means that the column space may change, but linear dependencies between columns do not. All right, so let us give the proof of this theorem. And we start with part 1. So let's recall that the row space of A is the span of its rows. So it's a span of R1 through Rm. Right, and so what we do here is we apply to rows elementary row operations, and we get a new matrix So we had the matrix A, and then we applied elementary row operation, and we get a matrix A prime with new rows. And so what we need to show is that this row space is equal to the span of the rows of the new matrix, R1 prime up to Rm prime. All right, so we consider three types of elementary row operations. So let's recall them. So we have type 1. So this is when we say that row I prime is equal to row I plus a constant times row j. Then we have type 2. So when we say that row I prime is k times row I, where k is a non-zero scalar. And type 3 is when we swap two rows. So we interchange row I and row j. We need to prove equality of two sets. And our standard method for proving equality of two sets is we show double inclusion. So we want to show that the set on the right is a subset of the set on the left, and that the set on the left is a subset of the set on the right. So now let's begin with type 1 elementary row operation. So this means that row I prime is row I plus a constant times row j, and row S prime is equal to row S for S different from I. So, all right, so we need to show that this span is a subset of this span. So what we do is we take an arbitrary vector in this set, and we want to show that it belongs here. So we say, let U be an arbitrary vector in row space of A prime. This means that U is a linear combination of the rows of A prime. So this means that we can write U as S1 R1 prime plus dot 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 SM Rm prime. Now, so what we have is that all rows of the new matrix except for row number I are the same as the rows of the old matrix. So we can write this as S1 times R1 plus dot 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 plus the interesting case is when we have row I, and row I prime is equal to row I plus constant times row j plus dot 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 plus SM times row m. Now, so then this can be written as S1 times row 1 plus dot dot dot, so SI times row I plus dot dot dot, and contribution of row j, so we'll have two terms. So we will have Sj times row j, and also Si times C plus SiC times row j plus dot 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 plus SM dot Rm. And what we see is that this expression is a linear combination of the rows of the original matrix. So this means that this belongs to the row space of the matrix A. And so what we obtained is that if we take any vector in the row space of A prime, then it will belong to the row space of A. So this means that we verified this inclusion, so that this set is a subset here. Now, instead of proving the opposite inclusion, so what we can say is that our elementary row operations are invertible, right? So this means that the matrix A may be obtained from A prime by applying the same type elementary row operation. But what we just proved is the following, that if we take a matrix, apply an elementary row operation, then the row space of the new matrix is a subspace or is a subset of the row space of the old matrix. So since now we can obtain an old matrix by applying an elementary row operation to a new matrix, so applying this argument to inverse elementary row operation, we obtain that the row space of the old matrix is a subset in the row space of the new matrix. So this means that because elementary row operations are invertible, then the second inclusion follows from the first one. And so now we have double inclusion between these two sets. So this means that these two sets are equal. And so we proved, well, for type 1 operations, so we proved this fact. Now, if we take type 3 elementary row operation, then so that only interchanges the order of rows. And clearly, the span, the set of their linear combinations, will not change. So this means that for type 3 elementary row operation, the equality of these two spans is obvious. And for type 2 elementary row operation, I leave it as an exercise for you to show that these two spans are the same for type 2 elementary row operations. So this would complete the proof of the first statement, so that elementary row operations do not change the row space of a matrix. Now, the second statement is something that we already proved. So when we justified our Gaussian elimination method, we had to show that the set of solutions of a system of linear equations does not change when we apply elementary row operations. And here we consider a special case. So we'll just look at solution set with the zero right-hand side. And since the solution set does not change when we apply elementary row operations, so a null space is the solution set of this system of linear equations. So this means that we already proved that elementary row operations do not change the null space of A. In order to prove part 3 of this theorem, that elementary row operations do not change linear dependencies between columns of A, we need to recall our 3 interpretations of a system of linear equations. So we had the first interpretation was just a system of linear equations. The second interpretation was the matrix form. So it was AX equals, well, in general to B, but here we're interested in the case when it's AX is equal to 0. And there is a third interpretation. So this is a vector form. And so we said that this matrix form is, or a system form, is equivalent to a vector equation. And this vector equation is x1 times column 1 of the matrix plus x2 times column 2 of the matrix plus xn times column n of the matrix. And in this case, the right-hand side is equal to 0. Now, so what we see is that this system of equations is equivalent to this vector equation. But what is written here? So here we wrote a linear combination of the columns, which is equal to a 0 vector. This is nothing but a linear dependency between the columns. So this equivalence tells us that linear dependencies between columns are precisely elements of the null space of A. right? So because this the solution set of Ax equals 0, so all vectors x such that they satisfy this equation. So these are elements of the null space. And so if we write x in this form, then so this vector of x can be interpreted as coefficients of a linear dependencies between columns. And since we know that elementary row operations do not change the null space of A, so elementary row operations do not change the null space of A. So this implies that the same elementary row operations do not change linear dependencies between columns. So the columns might change when we apply elementary row operations, but these sort of linear dependencies will be preserved. And this is exactly the claim of the part 3 of this theorem. So this theorem has a corollary that says that elementary row operations do not change dimensions of row space, column space, or null space of a matrix. So this means that if we apply elementary row operation, then the dimension of the row space of the old matrix is equal to the dimension of the row space of the new matrix. Now, for row space and for null space, this is completely obvious because these spaces simply do not change. And if the spaces do not change, then the dimensions do not change either. So we only need to show that this is true for the column space, because the column space may change, but here we know that linear dependencies do not change. And so this should help us proving that dimension of the column space is fixed under elementary row operations. So to prove that the dimension of the column space does not change, consider the set of columns. So let S be the set of columns of our matrix. What we proved in a previous lecture is that for any set of vectors, there is a subset which is linearly independent and has the same span. So this means that we can choose the set P, so it's a subset in S, so we just subset in the set of columns. So we can write P is the set of columns Ci1, Ci2, Cid, right? So just it's a certain subset of the set of columns such that P is linearly independent and the span of P is equal to the span of S, right? So we are choosing here a linearly independent subset with the same span. But what's the span of S? Span of S is the span of the set of columns. So by definition, this is the column space of A. And so what we get is that a set P is linearly independent and it spans column space of A. So this tells us that P is a basis of the column space of A. And so then what we claim is that if we take the columns with the same indices in the new matrix, so if we take column number I1 prime, column number I2 prime, so these are columns of the new matrix obtained by elementary row operation, so that this is a basis of the column space of A prime. So indeed, so in this theorem we saw that linear dependencies between columns are preserved. So this means that if this set of columns is linearly independent, then this set of columns is also linearly independent, because any linear dependencies here will become a linear dependency between these columns. And then, so we know, because P spans the column space, so this means that every vector in a column space is a linear combination of these columns, right? Or if we just take any other column in matrix A, then it will be a linear combination of columns from P. But because linear dependencies between columns are preserved, then so this other column in the matrix A prime will have the same expansion in these columns as we had here. And so this means that so this set of columns is linearly independent, and it spans the column space of A prime. And so now, since we obtained a basis of column of A prime, and we see that the number of vectors in this basis is the same by construction as the number of vectors in this basis. So this means that dimensions, which are number of vectors in a basis, is the same, right? So what we get is the dimension of the column space of A is equal to the dimension of the column space of A prime. And this also gives us a way how to construct bases in the column space of a matrix. Now, so next we're going to consider one example where we take a specific matrix and work out what are the bases of the row space, column space, and the null space. All right, so let's solve the following problem. So we want to find the bases for the row space, column space, and the null space for the following matrix. And so we know how the spaces change or do not change when we apply elementary row operations. So what we're going to do is we're going to simplify this matrix by bringing it to a reduced row echelon form. So as the first step, so we are going to eliminate entries under this pivot, right? So by using elementary row operations and subtracting multiples of the first row. So we say row 2 new is row 2 minus row 1. Then row 3 new is row 3 minus 2 times row 1. And row 4 new is row 4 minus 3 times row 1. So if we do this, we get the following matrix. Well, the first row is unchanged. Then the second row becomes 0, 0, 1, 2, 3. Then the third row becomes a row of zeros. And the last row becomes 0, 0, 0, 0, and 2. Okay, so we get this matrix. So then what we do is we say that row. So what we do is we switch row 2 and row 3. Right, and then after we do this, so the new row 3, we're going to multiply by 1/2. Right, so I'm just don't want to rewrite the matrices, so it's clear what we're going to get as a result of these two steps. So the matrix will be 1, 1, 1, 1, 1, 0, 0, 1, 2, 3, 0, 0, 0, 0, 1, and all zeros in the last row. So that's what we're getting here. So then, now this is row echelon form, right? So we have this pattern here. So now we eliminate entries above the last pivot. So we say that row 1 new is row 1 minus row 3, and row 2 new is row 1 minus 3 times row 3. So then we obtain the matrix 1, 1, 1, 1, 0, 0, 0, 1, 2, 0, 0, 0, 0, 0, 1, and 0, 0, 0, 0, 0. And so now we make the last step. So we eliminate the non-zero entry here. So what we say is row 1 new is row 1 minus row 2. And so the reduced row echelon form will become 1, 1, 0, negative 1, 0, 0, 0, 1, 2, 0, 0, 0, 0, 0, 1, and 0, 0, 0, 0, 0. Right, so this is reduced row echelon form. So since we obtained this last matrix as a sequence of elementary row operations from the first matrix, so then what we know is that the row space of the last matrix is the same as the row space of the original matrix. The null space of the last matrix is also the same as the null space of the original matrix. So this means that if we can construct a basis of the row space of the last matrix, then this basis will be the basis of the row space of the first matrix. Same for the null space. So if we construct the basis of the null space of the last matrix, this gives us the basis of the null space of the original matrix. And we have to be a little bit more careful with columns. So then we need to see how can we relate a basis of the column space of this matrix to the basis of the column space of the original matrix. Let us look at the row space. So for this matrix, we see that the row space is spanned by the first 3 rows. So clearly the last row does not contribute to the span because it's a 0 row. So this means that the row space of this final matrix is spanned by 3 vectors as opposed to the original matrix where the row space is spanned by 4 vectors. And moreover, so we claim that rows of reduced row echelon form are linearly independent. So let us check this. So suppose we take a linear combination of the rows of the first 3 rows of this matrix. So we multiply the first row by C1, the second row by C2, and the last row by C3. So what is this linear combination going to look like? So we take C1 times row 1. Well, I'll call it prime because, say, let's think that this is A prime. And this is A, right? So plus C2 times row 2 prime plus C3 times row 3 prime. So a linear combination of 3 rows is going to be a row. So the first entry of this row is going to be C1, right? So because we have zeros here. The second entry is also going to be C1. The third entry is going to be C2. Then the fourth entry is going to be minus C1 plus 2C2. And the last entry is going to be C3. Right? And so how do we verify linear dependency or independency? We take a linear combination of the rows and we must equate it to a zero row, a zero vector. Right? And so then we need to see, so if this linear combination is equated to zero vector, can we find solutions with non-zero values of our scalars? So this means that now we're equating this row to the zero row. But what does it mean? So this means that if we equate these two vectors, so looking at their first components, we see that C1 must be equal to 0. Looking at the third component, we see that C2 must be equal to 0. And looking at the last component, we see that C3 must be equal to 0. So this tells us that the only linear combination of these 3 rows that is equal to the 0 row is when all coefficients are equal to 0. So this means that only linear combination of these vectors, which is equal to the 0 vector, is when all coefficients are equal to 0. And so this means that these rows of reduced row echelon form are linearly independent. Why is it true in general? So it's true in general because in row echelon form, or in reduced row echelon form, we have these pivot entries, right? And so if we take a linear combination of these rows, say C1 times the first row, C2 times the second row, and C3 times the last row, then if we look at pivot positions, so we take this linear combination and see what is the component of this linear combination in the first pivot position. Well, it's going to be C1 because we'll have zeros in all other entries of this column. Now, if we take the component of the linear combination that corresponds to the second pivot, then we see that this component will only be C2 because this pivot is the only non-zero entry in this position. And likewise, for the last pivot column, we see that the last component of this linear combination is going to be C3. So this means that if we equate this whole linear combination to a zero row, so this forces all coefficients of this linear combination to be 0, just by looking at components of the linear combinations that correspond to pivot positions. And so this tells us that the only linear combination of these rows of the reduced row echelon form that is equal to the 0 row is when all coefficients are equal to 0. And so this means that this is a general principle. For any reduced row echelon form, the non-zero rows, right? So maybe I should say not rows, but non-zero rows. Non-zero rows of reduced row echelon form are always linearly independent. So now let us look at this set, right? So let's take non-zero rows of reduced row echelon form, R1 prime, R2 prime, and R3 prime, right? So what we know is that this set is linearly independent. So we have seen this. And so we also know that the span of this set is equal to, well, the row space of A prime, right? So because these are all non-zero rows of A prime. But by our theorem, this is the same as the row space of A. So what we constructed is a linearly independent set of vectors that spans the subspace that we want. So spans the row space of A. And so this means that non-zero rows of reduced row echelon form a basis of the row space of A, right? And so we have a linearly independent set that spans the row space of A. So that's the definition of a basis of the row space of A. So this means that, so we can write down, so the basis of the row space of A is so the set of three vectors. And because these are rows, I'll write them as rows. So 1, 1, 0, minus 1, 0. Then 0, 0, 1, 2, 0. And 0, 0, 0, 0, 1. So this set of three vectors in R5, right? So this is going to be a basis of the row space of A. And so the conclusion is that dimension of the row space of A is equal to 3, because we have three vectors in its basis. Now, next, let us look at the column space of A. So let us try to find the basis of the column space of A prime. In fact, because A prime is such a simple matrix, we can easily write down, so what is the basis of the column space of A prime. And here, so I claim that to construct the basis of the column space of A prime, I take the following columns. I take the first column of A prime. Then I take the third column of A prime. And I take the last column of A prime. Right, so this is C1 prime, C3 prime, and C5 prime. And so here I claim that this is a basis of the column space of A prime. Well, to show that something is a basis, we need to prove two things. A, that this set is linearly independent, and B, that it spans the right space. So for linear independence, this is obvious, because what we see is that this set of columns is a subset of the standard basis of R4. And for the standard basis, we know that the standard basis consists of linearly independent vectors, right? So there is only one vector that's missing here, 0, 0, 0, 1. And so what we know is that if we have a linearly independent set, then any subset is also linearly independent. And because the standard basis is linearly independent, so this subset of columns is also linearly independent. Now, let us show that this set of columns spans the column space of A prime. So for this, we need to show that every other column in A prime is a linear combination of these columns. But that is easy to see from this matrix, because what we can see is if we take the second column, then here it's just the same as the first column. And if we take column number 4, then what is it? So it's minus 1 times C1 and plus 2 times C3. Right? So what we see is that this column is so minus 1. So what we are saying is that if we take minus 1, 2, 0, 0, then this is equal to minus 1 times 1, 0, 0, 0 plus 2 times 0, 1, 0, 0. And so these are these vectors from the standard basis. And so this tells us that the fourth column of this matrix is a linear combination of the first column of this matrix and the third column of this matrix. And so this shows that every column in A prime is a linear combination of these pivot columns that we have chosen. And so this means that these pivot columns of A prime will be linearly independent and span the column space of A prime. So this means that this is a basis of the column space of A prime. Now, is this a basis of the column space of A? And the answer is no, it's not true. So because the column space does change when we apply elementary row operations. So to get the basis of the column space of A, so what we do is we take columns of A with the same indices. So we take C1, C3, and C5 from the original matrix. So this becomes the following set of vectors. So C1 is 1, 1, 2, 3. C3 is 1, 2, 2, 3. And C5 is 1, 4, 2, 5. Right? And so what we claim is that this set of columns is the basis of the column space of the original matrix. And our theorem said that linear dependencies between columns are preserved. So this means that here we had this linear dependency. We said that in this reduced form, column number 1 was equal to column number 2. So our theorem predicts that the same relation holds for the original matrix. So that column number 2 in the original matrix is equal to column number 1 in the original matrix. And we check and we see that this is true. Or, so this is a linear dependency between columns 4, 1, and 3 in the final matrix. So we say that the same thing holds in the original matrix. So column number 4 is equal to minus column number 1 plus 2 times column number 3. So this is the prediction of our theorem. Let us verify this relation. So we take minus C1 plus 2C3 for the original matrix. So minus C1, so this is going to be minus 1, minus 1, minus 2, minus 3, plus 2 times column number 3. Column number 3 is 1, 2, 2, 3. Now let's calculate this. So what we have is minus 1 plus 2, that's 1. Minus 1 plus 4, that's 3. Minus 2 plus 4, that's 2. And minus 3 plus 6, that's 3. And we compare it with column number 4, and we see that this is exactly column number 4 of the original matrix. So what's going on here is that, so in the original matrix, we might have some linear dependencies between columns, but these linear dependencies, they are hidden. So it's not obvious at all when we look at this matrix that column number 4 is expressed as a linear combination of column number 1 and column number 3. So when we look at the reduced row echelon form, these linear dependencies between columns are all uncovered. So here it's quite obvious that column number 4 is a linear combination of these two columns, and so here are the coefficients. It's minus 1 and 2. So here things are obvious and uncovered. And so this allows us, since we can see now using the reduced row echelon form, what are the linear dependencies between columns here. So what we do is, so we take a basis of pivot columns for the column space of A prime, and then the same columns in the original matrix, right? So we take column 1, column 3, and column 5. These columns will form the basis of the column space of the original matrix. So now we just keep the indices and go to the original matrix. And so in particular, we see that dimension of the column space of A is equal to 3. So because we have 3 vectors in the basis. So now we can summarize that basis of the column space of A is formed by columns of A corresponding to pivot columns, or to positions of pivot columns in row echelon form of A. So here, in fact, we don't need to go to reduced row echelon form, because if we are only interested in positions of pivots, then it's enough to go to row echelon form. However, if we want to uncover linear dependencies between columns, then we have to go to reduced row echelon form, so just to get these coefficients. So finally, let us look at the basis of the null space of A. So this means that we're looking at the set of solutions of AX equals 0. And this is something that we have done before. So what we do is we have to write down a general parametric solution in a vector form for this system of linear equations. So what we do is we classify variables into leading variables and free variables. And then we assign parameters to free variables. So leading variables that correspond to pivots. So we say that x1, x3, and x5. So these are leading variables. And all other variables, so that is x2 and x4, these are free variables. So now, we take our list of variables, x1, x2, x3, x4, and x5. So what we do, we assign parameters to our free variables. So we say that x2 is equal to s, and x4 is equal to t. And then we express our leading variables through these parameters. Now, what is equation number 3 here? So if we read this equation number 3, then it says x5 is equal to 0. So this means that x5 is going to be 0 and will not depend on the parameters. Then the second equation says that x3 plus 2x4 is equal to 0. And x4 is a free variable. So from here we see that x3 is equal to minus 2t. And so the first equation says that x1 plus x2 minus x4 is equal to 0. So which means that x1 is equal to minus x2 plus x4. And so this x2 and x4 are both free variables. So we get that x1 is equal to minus s plus t. So this is a general parametric solution of this equation ax equals 0. Now we write it in a vector form. So we write x1, x2, x3, x4, x5. And so we write it with separating our two parameters. So it's s times the following vector. So here we have minus 1, 1, and then 3 zeros. Right? Plus t times the vector 1, 0, minus 2, 1, 0. So this is the general parametric solution in vector form. So what does it describe? So this general parametric solution describes the null space, AX equals 0. And what it says, that the null space is a span of these two vectors. So it's the set of all possible linear combinations of these two vectors. So this means that the null space is spanned by these two vectors. But we claim that these two vectors are linearly independent. How can we see this? So we see that the components of this linear combination is given here, right? So these are the components of this linear combination on the right. And if we look at the free variables, so the free variables correspond to our parameters. So if we equate this whole column to 0, so if we equate every component to 0 here, then this means that we equate our free parameters to 0, because if we look just at free variables, then we see that this equation will say that s has to be 0, and this one says that t is equal to 0. So if we assume that a linear combination of these two vectors is equal to 0 vector with 5 components, then this would mean that both of our parameters have to have value 0. And so this means that the only linear combination of these two vectors which is equal to a 0 vector is when these parameters are 0. So the conclusion is that this pair of vectors is linearly independent and it spans the null space. So this is a basis of the null space. So we get that the basis of the null space of A is the set of these two vectors. So the first vector is -1, 1, 0, 0, 0. And the second vector is 1, 0, -2, 1, 0. So the answer is that this is the basis of the null space. And so what we get is that the dimension of the null space of A is equal to 2. So the null space of A is two-dimensional because we have two vectors in a basis. And geometrically, this null space will be a plane. So we have these two directing vectors, right? And these two vectors will span a plane. So this is the description of the null space. So here we found the basis of the row space, the column space, and the null space for this matrix. So what we see is that these ideas generalize to any matrix. So that here, so if we want to find the basis of a row space, then we go to reduced row echelon form, and rows of reduced row echelon form will form a basis of the row space of A. So to find the basis of the column space of A, so we again go to reduced row echelon form, find the locations of the pivots, and take the matching columns from the original matrix. So this will be the basis of the column space of A. And to form a basis of the null space, so we write down our general parametric solution in a vector form. Then these vectors that we obtain, that are kind of vectors that correspond to each three parameters, they always will be linearly independent, right? So because of this idea that we look at free variables to establish linear independence. And so they will form always a basis of the null space. So what can we say in general about dimensions of these spaces? So let's look at dimension of the row space of A. So our definition was that the dimension of a space is the number of vectors in a basis. And here we say that a basis of the row space of A is formed by non-zero rows of the reduced row echelon form of a matrix. Now, what is the number of non-zero rows in reduced row echelon form? So we know that every non-zero row starts with a pivot. So this means that dimension of the row space of A is equal to the number of pivots in reduced row echelon form of A. Now, let us look at dimension of the column space of A. And dimension of the column space of A is the number of vectors in the basis of the column space of A. And here we say that the column space of A is formed by columns of A that correspond to pivot columns in the reduced row echelon form of A. And so here, so the number of pivot columns in reduced row echelon form of A is also equal to the number of pivots in reduced row echelon form of A. And what's the dimension of the null space of A? Now, null space of A, the vectors in the basis of the null space of A corresponded to free variables, right? So this means that this is equal to the number of free variables. And so now we can take these equalities and we can summarize them in one important theorem. We have theorem / definition. And this theorem has two parts. So dimensions of row space and column space of a matrix A are equal. This dimension of either column space or row space is called the rank of A. And denoted rank of A. And the second part of this theorem says that dimension of null space of A plus rank of A is equal to the number of columns of A. For the proof, so the first part follows from the fact that here we establish that dimension of the row space and dimension of the column space are both equal to the number of pivots in reduced row echelon form of A. So this tells us that these two dimensions are the same, and so this number is called the rank. So for example, for this matrix, the rank, or for either A prime or rank of A, so these two matrices had rank 3. So we compute the rank by counting the number of pivots, but it's important to remember that rank really means dimension of the row space or the column space. And so now, if we look at the last formula, so what do we have here? So here we have that the rank of A is the number of pivots, but the number of pivots is equal to the number of leading variables. And the dimension of the null space is equal to number of free variables. And if we add the number of free variables plus the number of leading variables, then we get the total number of variables. But we know that for a system of linear equations, variables correspond to columns. So the number of variables is equal to the number of columns. So this trivial equality that the number of variables is equal to number of free variables plus number of leading variables, so this is interpreted as dimension of the null space plus the rank of a matrix are equal to the number of columns of A. And for this example, so what we had is we had dimension of the null space of A was 2, right? So we had 2 vectors in that basis. And so if we add, so dimension of the null space plus the rank of a matrix, so then we get 5, and this is equal to the number of columns in these matrices. So here, so the takeaway is that so the dimensions of the row space and column space are the same, and this number is called the rank of a matrix. And if we add rank with the dimensions of the null space, then we get the number of columns. So this equality, of course, can be played around, right? So this could say that dimension of the null space is equal to number of columns minus the rank of A. So we can play around with this equality. All right, so let us look at the following example. So we need to find a linearly independent subset R in a given set of vectors such that span of R is equal to the span of S. And here we have 4 vectors in R4, here we have 5 vectors in R4, so we know that this set of vectors is linearly dependent. And we actually had a theorem in a previous lecture that said that such a subset always exists. So what was our method of proof? So we said that if we have a linearly dependent set, then we can discard vectors one by one until we reach a linearly independent set. So however, this algorithm can work, but it's not the most computationally effective. And the computationally effective way is what we discussed today. So what we want to do is we want to interpret this span as a column space of a matrix. So what we say is form a matrix by placing given vectors as columns and find a basis of the column space of A, right? So now, so if we form a matrix by placing these as columns, so then you will quickly see that I have just recycled the matrix from the previous example because I'm lazy and I don't want to do row reduction. So, but nonetheless, what's important is the conclusion that we make here. So here we have the matrix. So the important point of our procedure of finding a basis of the column space of A is that this basis always consisted of the columns of the original matrix. And here our method was take this matrix, find its reduced row echelon form, look up locations of pivots, and say that so this basis of the column space of A is B, which consists of column 1, column 3, and column 5. So these are locations of pivot columns in the reduced row echelon form. And so this means, and this column space of A is the span of S, right? So because if we place these vectors as columns to form a matrix, then the span automatically becomes the column space of A. So this means that this column space of A is the same as span of the set S. And so here our algorithm tells us how to obtain the basis of this of the column space of A. So this means that, or maybe I should call this R, right? So this means that the span of R is equal to the column space of A, and thus it's equal to span of S. And so this set of columns is linearly independent. And so what we see is that the answer to this question is that R is the first, third, and the fifth vector from this set. So 1, 1, 2, 3, 1, 2, 2, 3, and 1, 4, 2, 5. So this selection of this subset is determined by positions of pivots in reduced row echelon form. So now, so we already mentioned this before, so before we said that we have this principle that if we want to say something about vector equations, then form matrices by placing given vectors as columns. And we come here to exactly the same conclusion, that if we want to find a basis, a subset of a given set of vectors, which is a basis of their span, then we should form a matrix by placing these given vectors as columns and then do something. And here it's important that we use columns and not rows, because in this method here, when we look for the basis of the row space, so this basis of the row space did not consist of the rows of the original matrix. So it was some rows only of reduced row echelon form. Whereas when we look at the basis of the column space, our algorithm automatically produced columns of the original matrix that were linearly independent and formed the basis of the column space. And so this gives us the way how effectively solve this problem that we kind of discussed theoretically last time. But now we have an efficient computational algorithm for finding a linearly independent subset in a given set of vectors, such that this smaller subset spans the whole span of the original set of vectors. So that's how we solve this problem. All right, so now let us look at the following problem. So we want to find the basis of a subspace U in R4 given as a solution set of this system of linear equations. So here we have a homogeneous system of linear equations. So what we know is that the solution set is always a subspace. And once we have a subspace, we can find this dimension of a subspace and its basis. And then we had a theorem in the previous lecture that said that if we have a basis of a subspace, then we can always extend it to the basis of the whole space by adding extra vectors. And so we want to do this in this particular example. So once we constructed the basis of U, we want to extend this basis to a basis of R4. So this means that we want to obtain a basis of R4 that includes the basis of U that we have constructed. Now, so the first part is more straightforward. So here we need to find the basis of the solution space. So this means that, well, we just write down the matrix of this system. So it will be 1, 1, minus 1, 1, and then 1, 2, 3, 4. Right? And so what we want to find here is we want to find basis of null space of A. Right? So this will be, so this null space of A is precisely the subspace U in question here. And so what we find the basis of the null space by basically writing down general parametric solution of this system of linear equations in vector form. And to do this, we need to do row reduction. So we say row 2 prime is row 2 minus row 1. So we get matrix 1, 1, minus 1, 1, 0, 1, and then 3 minus negative 1, that's 4, and 4 minus 1, that's 3. Right? And then to bring it to reduced row echelon form, so now we say row 1 prime is row 1 minus row 2. And we get the matrix 1, 0, minus 1 minus 4, that's negative 5, and 1 minus 3, negative 2. 0, 1, 4, 3. All right, so now this is reduced row echelon form. And so now we have our pivots. So to write down the solution, we identify free variables and leading variables. So here we see that x1 and x2 are leading, and x3 and x4 are free. And so we write down the general solution by assigning parameters to free variables. So we say x3 is s, x4 is t, and then from the first equation we see that x1 is 5s plus 2t, and from the second equation we see that x2 is minus 4s minus 3t. And so then if we write this in the vector form, x1, x2, x3, x4, so the s vector is going to be 5, negative 4, 1, 0, and t vector is going to be 2, negative 3, 0, 1. And so the answer is that the basis of U, which is the same as null space of A, is a pair of vectors. So the first vector is 5, negative 4, 1, 0. And the second vector is 2, negative 3, 0, 1. So now we come to the second part of this problem, which is more challenging. So now we need to take these two vectors and extend it to the basis of R4. And we know that the basis of R4 will contain 4 vectors. So we need to add 2 more vectors to obtain a basis of R4. And here we're going to do the following trick. Let's form a matrix by placing these 2 vectors as columns. So we have 5, negative 4, 1, 0, and 2, negative 3, 0, 1. And then I will add more columns by placing the standard basis vectors of R4. So now I obtain this larger matrix. What can I say about this matrix? What's the column space of this matrix? So the column space of this matrix is surely equal to R4, because here we have columns that form a basis of R4. So this means that the columns of this matrix will span R4. And now, if I want to find the basis of the column space of this matrix, then because I placed my 2 columns first, so these 2 columns will be selected when we construct the basis of the column space of this matrix. So this is what we're going to do. So now we're going to use our standard algorithm for finding the basis of the column space of this matrix, and the prediction that the basis of the column space of this matrix will have 4 columns. Now we only need to decide which ones. So to do this, we do elementary row operations. And so here, because of the structure of this matrix, what's convenient to do is, as our first step, I'm going to swap row 1 with row 3, and row 2 with row 4. So my new matrix is going to be 1, then 3 zeros, and then 1, 0. Then the second row is 0, 1, then 0, 0, 0, 1. And then we have a row 5, 2, 1, 0, 0, 0. And then negative 4, negative 3, 0, 1, 0, 0. And so now we do row reduction. So we need to eliminate this 5 and negative 4. So we say row 3 new is row 3 minus 5 row 1, and row 4 new is row 4 plus 4 row 1. So the new matrix will be 1, 0, 0, 0, 1, 0, then 0, 1, 0, 0, 0, 1. Then, so we subtract 5 times row 1. So we get 0, 2, 1, 0, negative 5, 0. And here we add 4 times row 1. So we get 0, negative 3, then 0, 1, 4, 0. So this is this matrix. Now for the next step, so we use this pivot and we apply the following elementary row operations. So we say that new row 3 is row 3 minus 2 times row 2, and row 4 new is row 4 plus 3 times row 2. So what is the matrix? So we get 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1. Then here we subtract 2 times row 2. So we get 0, 0, 1, 0, negative 5, negative 2. And for the last row, we add 3 times row 2. So we get 0, 0. Here we get 0. Then here we have 1. Then 4. And 3. All right. And so this matrix is in row echelon form. Well, this is reduced row echelon form, but really all we need is row echelon form. And so what we see is we see that the first 4 columns have pivots in this. And so this tells us what's the basis of the column space of the original matrix. So what we get is that the basis of the column space of A, which we know here that this is R4, is the first 4 columns of this matrix. So this will be 5, negative 4, 1, 0. And then 2, negative 3, 0, 1. Then 1, 0, 0, 0. And 0, 1, 0, 0. And now we see that using this trick, we solved our problem. So we obtained a basis of R4 that starts as a basis of U, right? So this was the basis of U here. So we have a basis of a subspace, and now we added 2 more vectors, right? So because we need 4 vectors to get a basis of R4. So by adding these 2 vectors, we obtain the basis of R4 that extends the basis of U that we found in part A. And so what we see is that this method is based on the idea of the column space and the way how we find bases of column spaces. So often when we solve problems about vectors in R4, we still use matrices, and we use our technology for matrices. So our idea is that we want to construct matrices for which the column space has the right interpretation.